So if you think back to the genesis of the Industrial Revolution and as it developed through the 19th century, one of the things that strikes me is everything was on a mega scale. You know, giant coal mines, steam engines, machinery, factories. But industrial innovation these days happens at a very different size scale, the ultra microscopic. So now industrial innovation happens arranging individual atoms or working with folding sheets that are 1 atom thick. It's a completely new and different world, but it has the same sorts of things driving it as the Industrial Revolution did. Cagri Ayranci is working in this. It's even the nano world, not the ultra microscopic. He's in the Department of Mechanical Engineering at the University of Alberta, and he's going to give us some insights into what it's like to work in this modern industrial world. Cagri.
Thank you, Jay. Hello. All right. Hello, everybody. So my name is Cagri Ayranci. I don't write it that way. As you can see, it's written Cagri. I was born in Ottawa, Ontario, but from the very thick accent, you can imagine that after 5 years, we went back to Turkey, and I came back for my master's, undergrad and master's, and we stayed still since then. I'm originally from a coast city in Turkey called Antalya. It's on the Mediterranean, so just like Thava was saying, you know, I'm coming also from plus 45-ish degrees to minus 45. Interesting. Antalya is the city that gives both my daughters their names, Talia and Alanya. So that's a very nice city if you have a chance to visit. As I mentioned, we came back in '99, and I did my undergraduate and master's at University of Ottawa, the biggest bilingual university in North America. I still don't speak French, but I did get married to a francophone, which I covered that basis. So after that, I came to University of Alberta to do my PhD in mechanical engineering department. Then I went to UBC. So from all the way east to west, UBC, I did my postdoctoral fellowship there. And then in 2012, I got hired back from University of Alberta as an assistant professor, and I'm here since then. Now, in general, I work with fibrous composite materials. I work on braided composite materials. These are materials, if I can get the video, please. Braiding is a very old technique that's used for textile manufacturing, but of course now we are using it for advanced materials. What you see is the production of a polymeric reinforced rebar that is alternatives to steel rebars in civil engineering applications. I have to say the alternative, otherwise civil engineers get very upset with me. So it's an alternative rebar. On the right, that small figure that you see is we are the first group in the world that showed a 3D braided arch wire for dental applications, and we showed the production and tailorability of the mechanical properties. My other work is on shape memory polymers. These are polymers that can have a temporary shape and that's assigned, and then we can recall the original shape you see there in the straight beam. My third area of research, which I'll be talking a little bit today, is electrospun formation and characterization of electrospun nanofibers. These are very, very small fibers we'll be talking about. And additive manufacturing, 3D printing using FDM technique. Here you see two very, very small miniature kayaks printed in my laboratory, again using shape memory polymers for these applications. Now, as you can see, one thing that is common here is everything that I do depends on fibers. So I'm a fiber composite guy. And today what I would like to talk to you about is a fiber that really excites me a lot. It is actually a nanofiber. It is called cellulose nanocrystals, CNC. If you go back, cellulose is the most abundant natural biodegradable renewable polymer in the world, and CNC, cellulose nanocrystals, are basically obtained from the crystalline regions of these cellulosic fibers. AITF here in Alberta has one of the very few pilot plants in production of CNC, and I feel very, very lucky to be able able to have access to the CNC. So if you look in general, CNC on the left-hand side, that white cotton-looking stuff is actually the CNC, the cellulose nanocrystals. When you look at it, it clumps together. It looks like cotton, as I said, or cotton candy, whatever you want to call it. But if you actually go and take a close look at it under the microscope, scan electron microscope on the right-hand side, you will see that these are actually very, very small nanocrystals. So all those rods that you see are nanocrystals, cellulosic nanocrystals. And just to give you an idea as to the size of these, there's a chart there. You can see human hair is on the right-hand side, CNC with the red on the left-hand side. Human hair is approximately, roughly 100,000 nanometers. The CNC is roughly 10 nanometer in diameter, so a very, very small dimension. So, viruses, bacteria there, so CNC is very, very small. So we need to find ways to put this into the materials. Now, why? Because CNC has very great mechanical properties, and that's the thing that excites me as a composite material engineer, composite materials professor. It gives 2 times the stiffness of aluminum, 10 times the strength of stainless steel. So it's a really, really great material, but very small. You can't just take and pull on it, right? So you need to be able to put it into the material, and you need to be able to disperse it in the material very well. You can't let it clump or agglomerate in one portion and the other portions don't have CNC. So it is really, really important to be able to put it homogeneously into the material. And this is only possible when you properly surface modify the CNC and allow it to disperse within the material. And that's why I actually collaborate a lot with chemists, with chemical engineers, and etc. The projects that I'm going to be talking to you about, CNC has a lot of different applications. Films, ropes, small fibers, foams, as I will be talking about. Today I will be talking about 2 of the applications that I'm doing in my laboratory. This is related to a project that is supported by Alberta Innovates Biosolutions, and it's called Nanocrystalline Cellulose Reinforced Foam Core Sandwich Composite Structures. Why NCC? Because when we wrote the project 2.5 years ago or so, it used to be called NCC, now it's CNC, so it's the same thing. So if you look at the a sandwich structure, you have a skin layer, you have a foam core, and in between you have an adhesive layer. In this project, we are trying to put the CNC to reinforce into the adhesive layer. So we are trying to produce CNC reinforced electrospun adhesive layer, and we are trying to put it also into the foam core. So we are trying to make CNC reinforced foam core structures. Now, first, electrospinning. Let's talk a little bit about electrospinning. It is a very simple technique, very old technique. First patent is around 1904, I believe, 1912. But it started to get popularized around 90s and 2000. Now, it is a very, very popular technique to produce polymeric nanofibers. We have quite a bit of parameters that we can play with so that we can tailor the end properties and morphology of the materials. If I can get the video, please. So on the right-hand side, you see that when the video is running, you will see the end product when we electrospun a basically randomly distributed fiber mat. You can see it's like a cloth, actually. It's a randomly distributed fiber. It can be produced very, very quickly, and it is fairly strong, depending on the polymer that you're using. But of course, it becomes much, much, much stronger when you put CNC in it, and that's what we are interested in. So that cloth-like structure, if you actually zoom in there with a SEM, you will see these small, small, small fibers, which sub-micron or nano diameter, and we are actually trying to put the NCC into those small fibers to even further improve. Now, in this project, we are trying to reinforce the polystyrene with NCC, and so far we actually got quite good results in terms of the increase in the modules of the fibers. This is modulus versus modified CNC concentration, and even from 0% CNC to 2% CNC, we are getting approximately 9 times increase in the elastic modulus, which is absolutely fantastic for us. The second one, again, this time is the foam core for the sandwich structure. I'm going to be talking about expanded polystyrene foams, which is EPS. EPS, we are actually very familiar. Whenever you buy a computer, a TV or something, the foam that comes in it, the protective foam, is EPS. It's not the only use, of course. It's one of the most widely used foams in the world, so there's a large market for it. So we take, if you look at the step one, we take the EPS resin. We expand those beads due to the pentane in it. It's almost like a popcorn. It pops, it increases in size, sometimes 20 to 30 times. And then we basically take them and mold it into a shape. Now, what we are trying to do, if you take a cross-section of that foam, you will see the cellular extractor. So what we are trying to do is we are trying to put CNCs into there to improve the mechanical properties, more particularly the compressive modulus and etc. Now, we are right about here in our project right now. So the preliminary results are actually very, very encouraging. You can see the specific modulus of the foam with respect to CNC concentration. We have a steady increase. We are going approximately 60% increase with even 1% CNC. Of course, we still have a wide spread in data, so we are conducting more experiments, but this is very, very promising. And also, the results are so promising that there is a Calgary, around that Calgary region, there is a big EPS producer. It's one of the biggest EPS producers in North America. They are already very much interested in the product, so we will be talking to them in terms of commercialization of this product. The scale of use, you can imagine, we can use it in insulating roofs, floors, walls, concrete forming applications, and structural lightweight fill or road embankment construction applications. So you can see if we can increase the mechanical properties, that means that we can use actually lower material. Just think about the volume of these being transported from the factories to the sites. It is going to bring a great advantage to the industry. Where are we going? We are going to be seeing CNC to be used in many, many different applications down the future. Biomedical devices, catheters, and etc. Composite ropes, textiles. We are starting a project on that. Filtration purposes and controlled drug delivery in pharmaceutical applications. So these are all the things that we will be seeing down the road in the future. And before exceeding too much my time, I would like to thank, first of all, my co-investigators, Professor Yaman Bölük and Professor Mark McDermott from University of Alberta, as well the research team. I would like to acknowledge all of them, including Alberta Innovates and Technology Futures team, Dr. Behzat Ahvazi and his group, and Dr. Christophe Danuma. And of course, these are all happening with the funding that is provided by AI Bio to us, not only to the project, but also to the pilot plant that is built in AITF under the AI umbrella. Just to give a very, very small history, when I first came in 2012, I was really dying to get my hands on CNC. It was a novel product. I really wanted it. And you can't find it here and there. A couple of research laboratories are synthesizing it. And all of a sudden, I gave a call to AITF. And they said, OK, yeah, we'll send you some. Of course, I had to sign my life away with an NDA, non-disclosure agreement. But I got 5 grams. 5 grams, I was extremely happy. That was, we actually published 2 conference papers, 1 journal paper from that 5 grams. I still have a little bit. Just to let you know what happens with AI biofunding and AITF support and all the research going on. Now, I basically call my contact, Dr. Behzat Ahvazi, who's the team lead there on CNC. I said, Benji, I need a little bit CNC to finish this project. Can you send me? He said, yeah, sure. Is half a kilogram enough? From 5 grams to half a kilogram, and this is helping us to do more and more research. This is helping us to connect to industries such as the foam industry and etc. And we truly appreciate the support. Thank you.
So I just want to pick up on the labyrinth idea that Jonathan gave us. And you gave us a huge variety of potential uses, and you showed us a graph where you say, so far the results are encouraging. So At what point, though, do you have to jump off a horse that isn't running fast enough? Do you know, like how do you make those decisions of all these promising leads, this one we got to put our efforts in because that one isn't as promising?
Well, I think it's how do you do that? Doing a really good literature review and understand what is capable, what can you do with this material. Now, for example, when this first came out, people were trying to put 20% of CNC into a material. And actually, there is an optimal point after, depending on the polymer, after 5% you start decrease. So I see my best results in electrospinning in approximately 2.5%, 3%, 2% sometimes. So you don't want to put too much. So what is important is to create design curves for design engineers so that they know what is the best point of utilizing this, as well as if I use this much, if I get this much benefit in mechanical properties, for example, how much is that going to cost me? So I think that's the important thing that needs to be, and so far CNC is a tremendous material, I think. It has very good promise.
Great. Thanks again, Charlie.
Thank you.